Hey, Nyla. Cheyenne, good to see you. How are you both?
I'm good. How are you?
I'm doing very well, thank you. Having a good day. Give me 1 second here.
Yeah, it's still a bit earlier than I wake up.
Oh, what time is it where you are?
Um, it's 9, but
9.
I woke up at what, 6, I think.
Oh, wow. Yeah, that's an early morning. I'm usually somewhere between 6 and 7. That's a good time. I'm a morning person. I like the mornings. Early to bed, early to rise. What did Ben Franklin say? Makes a man healthy, wealthy, and wise. Yep.
You and my sister would get along great.
Yeah. All right. Good to see you today. Oh, it's not Tuesday. Your shirt says Tuesday. Is it Taco Tuesday? Is that I see a taco on that shirt too. Yeah. Oh, there you go. Taco mode or Tuesday mode. Yeah. That's great. Yeah. If it's Tuesday, I shouldn't be here. So bye. I'll see you guys tomorrow. Nope. It is Wednesday. It is Wednesday. All right. Hopefully nobody's having trouble getting in. Let's see here. Okay, Muhammad is here. We have 5 more students that should be joining us. Nobody let me know they weren't coming. Remember, for those of you who are here and those who watch this later, if you, oh, there's your cornstarch, cool. Yeah. If you know that you're not going to be in class, let me know, because then you get an excused absence as opposed to an unexcused absence. So always let me know in advance. Now, again, I don't take off points if you don't come to class. I just give you a few extra if you are a consistent attender, if you're someone who comes usually and participates in the class. So do any of you have any questions from last week? I know it's kind of early. You've only had a few lessons. All right. If you don't, I'm going to go ahead and get started. So I like to start right on time. And that also rewards those of you who are on time. I always appreciate it when you are on time for class. So let me share my screen. Please let me know if you cannot see where it says physical science. Everybody can see that? Okay, wonderful, wonderful. So as you hopefully know, we use an online resource called Flexbooks for the content for this course. Now, most of the time I've placed the Flexbook right into the lesson, and there's a link at the bottom of the page in a yellow box. I'll show you in just a second what I mean. And that will show you where the Flexbook pages came from that we use. So I want to spend just a minute showing you all the really cool stuff that Flexbooks has. So let me drag this in. So this is your physical science homepage. If you click where it says assignments, and let's take a look at one that is due this week. So we'll come down here. Let's look at the one that's due Friday. So we'll look at evaporation right here. This one, take a look at that one. Evaporation, condensation, sublimation, and deposition. So if you look here, this is the lesson. You read all the way through this, and then at the very bottom of the page, you'll see yellow box. This will be in all of the lessons that are taken from Flexbooks. And then there's links here. These are clickable. So if you want, you could always go to the Flexbook and read it there. If you'd prefer to read it there instead of reading it here, you can. Now, the thing is, I do make some changes. Sometimes I add some things. Sometimes I take away things or I clarify things if I think that they're not written in a very meaningful way. But you can always go see that Flexbook if you want to. Now, the thing is, there's a lot more to Flexbooks than just the text on the page. So the text on the page is where you would see read right here. If you click one of those links at the bottom, you'll see read, and you can click that and go to that lesson. But there's also interactives, there are practice problems, there are real world issues. So there are more. Sometimes there will be a video, there might be more things. Sometimes I use these, sometimes I don't. This practice is a really good thing to use. The practice is there to let you see if you understand the lesson. It's not graded, and unless I assign it as a lesson, it isn't a graded assignment. So you can go there and check and see if you understood before you take the quiz in Canvas. So a lot of the quiz questions I take from the practice problems right here. So doing that will also help you in the quizzes that we do. Then there's the real world things that are often fun. Sometimes we'll use those in our live classes. Sometimes I will assign them for you to read. Let's take a look at what a Plix looks like. So how hot is boiling water on Mount Everest? So this is a little bit of an interactive. So for this one, all we're going to do is raise the elevation by clicking on this red, and notice what happens to the boiling point and the atmospheric pressure as I take the elevation higher. You can see boiling point and pressure go down. As I take them down, they go back up. Now this is an easy one. That's all there is to this one. But you can also click the challenge me, and it'll ask you some questions about what you're doing. So again, nothing is graded unless it's in very specifically mentioned in Canvas that it is graded. But it's nice to, if you have more time and you have a bigger interest in something that we're learning about, going to the Flexbooks and seeing what else they have to offer, I think is a really great way to extend your knowledge, your information. All right. One thing I want you to keep in mind as you send me text messages, if you send me a message through Canvas inbox, be as specific as you can to help me help you as quickly as possible. If you're asking something about one of the Flexbook page numbers, tell me the page number, tell me the name of the lesson. Like, let me go back to this one. So if we were to take a look here, the name of this lesson is 1.7 state changes. All my lessons are numbered, which keeps them in order. So you could just say, I have a question about lesson 1.7, and then tell me what your question is and give me as much information as you possibly can so that I can get the help to you as much as possible. So we don't go back and forth before I figure out what it is that you're asking for. All right. I told you last week that we're going to be paying some attention to grammar as we go into the future now. At some point here in the next week or so, I'm going to start taking off points for grammar and spelling errors. I'll let you know when that happens. And it won't be a lot of points. It might be like 1/4 of a point on a question if there's a couple of errors in it. So it's not a lot, but it's enough that I hope it encourages you to start using proper grammar when you're doing your schoolwork. When you're submitting something here, when you're typing in the chat box here, you can type however you want. You can use chat speak as much as you want to. If you are sending me a Canvas inbox message, I'm not going to grade that. So that doesn't have to have perfect spelling, perfect grammar. But when you're turning something in for grading, then you want to make sure that you are using good spelling, using good grammar. And I've noticed a couple of common errors that students make. So I'm going to spend a little bit of time talking about them. These are the things that I will be grading on. There's a lot more to good grammar than just this, but this is what I'm going to be looking for. All right, here's why it matters, because one comma can save Grandpa's life. Let's eat Grandpa, or let's eat Grandpa. In one, you're having Grandpa for dinner, and the other, you're inviting him over. And I like this little cute one here. A panda eats shoots and leaves, unless it's a tactical panda, and then it eats shoots and leaves. All right, so what are we going to be looking for? I'm looking for capitalization of a few things. Always capitalize the first word of every sentence. Always capitalize the personal pronoun I, and always capitalize the names of specific people, places, and things. So don't use a little lowercase I when you're referring to yourself. Use a big I, the uppercase I. And always capitalize the first word of every sentence. Speaking of sentences, I want your answers to the test questions, anything you have to write out, to be in a complete sentence. So every sentence has two essential parts to it. It has what the sentence is about, called the subject, and it has what's happening, called the predicate. Usually a predicate is a verb, so we'll say verb. We'll say subject and verb is what it has to have. So every sentence needs to have a subject and verb like this. The flower is the subject, bloomed is the verb. Bob is the subject, painted is the verb. The girls on the team is the subject. We're all good students is the predicate because it's got a verb and other words as well. So give me full sentences. Do not begin a sentence with the word because. It's just best not to. There are a couple of situations where it's okay to do so, but they're pretty complicated. So for my class, let's just not do it unless we're talking. Again, when we're having a conversation here and I say to you, why did the plant die? It's fine for you to say because we didn't water it. Because is fine when you're in a conversation, but not when you are doing written work. Then finally, punctuation. Always end a sentence with some kind of punctuation. If it's a statement, it has a period or an exclamation point. If it is a question, it has a question mark. All right, now these are the most important ones for my class. So they're the ones that I'm going to grade you on. And here they are all together. Capitalize the first word of every sentence and the personal pronoun I. Use full sentences that don't begin with because, and make sure that you use punctuation at the end of your sentence. All right, I want to do a real quick let's get acquainted activity, just so that we can get to know each other a little bit. We'll do this each lesson for the first couple lessons. So I'm going to put a question in here, and I want you to type your answer into the chat box. All right, first question. Using just one word, name something that makes you happy. I'll read them as you type them in. Cats. Nyla likes cats. Food. Science. Wick, I love it. Lego. Boxing. Wow, do you like to box, Bella, or you like to watch it? Boba. You mean like boba tea, Allison? I love boba tea. Yeah, that's good. That's good. Excellent. All right, here is your next. You like to box. That's really fun. Awesome. Protect your face. Neuroscience, especially, Wick. Yeah, that's a very, very cool field. All right, here's your next question. What is your least favorite food? The one that comes to mind when you think, ew, I don't like that. Mushrooms. They're one of my favorites, Nyla. I have mushrooms almost every day. In fact, I grow mushrooms sometimes. I grow my own. Nobody else has a food they don't like? Vegetables. All vegetables, Cheyenne? You're going to put them all in the same category? You don't like any of them? Vegetable leaves, like lettuces? Yep. Well, hopefully you guys eat a lot of fruits because you need to get those nutrients from the vegetables. So you can get a lot of them from fruits as well. All right, your next question. If you could have 25 hours in each day, what would you do with the extra hour? Yeah, sleep. Sleep and study. Sleep. Yeah, sleep is a common one. Americans don't get enough sleep. As a general rule, we are sleep deprived. Not a good thing. Sleep's really important. Getting that extra hour would be a good idea. All right. How about this one? If you could be in the Guinness Book of World Records, what record breaking feat would you attempt? Wow, look, I have mushrooms on my cup. That's how much I love mushrooms. What record-breaking feat would you attempt? What would you like to be remembered for in the Guinness Book of World Records? Most boba tea made, most cookies eaten in a minute. Oh, in a minute. Wow. Anybody else? Making the most secret rooms in a house. Most cats fostered. So do you foster cats, Nyla? No, but you want to. All right. All right. One last question. Using just one word, name something that drives you crazy. Sibling, sister, brother. Aw, you'll be best friends someday. Right now, probably not, but when you're adults, you'll probably be best friends. All right, let's jump into talking about the states of matter. So you learned about the states of matter last week, but this week you're going to be learning, the rest of this week, you'll be learning about how matter can change states or change phases. And remember that that change really depends on primarily the temperature. Pressure is involved too, but primarily temperature is what makes a difference. So remember, we find matter in different states on Earth: solid, liquid, gas, and a little bit of plasma. Mostly, we find solid liquids and gases on the Earth. Now, it's really important that we remember that everything that has mass and takes up space is matter, right? Matter is made up of these tiny particles like atoms and molecules. Now, when we use that word particle, we might be referring to an atom, we might be referring to a molecule, but when we use the word particle, we're talking something very small, a very small part of matter. That's what the word particle means. It's become more common in physics and physical science classes to use the term particle. So we'll be using that throughout the course. Just remember that can mean atom or it can mean molecule. Remember that these particles, whether they're an atom or a molecule, the particles are always moving. They're always in motion. The type of motion that all states of matter has is called vibration. So even something solid like my computer mouse doesn't look like it's moving, but the particles that make up my computer mouse are moving. They're always constantly vibrating. All matter is constantly moving, at least a little tiny bit. Now, we have a name for the energy of motion. That name is kinetic energy. You can see here the state the matter's in, whether it's solid or liquid or gas, depends on the kinetic or movement energy that the particles have. The more kinetic energy we have, the more the particles move and the higher the temperature. The less kinetic energy, the lower the temperature and the less motion we have in those particles. So as we go from the top of this picture to the bottom right here, the kinetic energy is going up because they're moving more. As they move more, kinetic energy is more. As they move less, kinetic energy is less. So here they all are again. We have solid, liquid, and gas. Remember that these particles, even the solid ones that look like they're holding still, are always in motion. Always, always. Even the most solid objects, like a chunk of rock, the particles inside that rock are in motion. Now, the motion of the particles is such an important concept in physical science that it has its own name. We call it thermal energy. Thermal energy is the movement of went too far. The movement of particles. It is the term we use to describe the kinetic energy or the moving energy of those moving particles. Now, thermal energy is the movement of particles. Gas has the most thermal energy, so gas is going to have the highest amount of kinetic energy as well. Gas is going to have the most, solid's going to have the least. Taking a look at it here, let's be sure we understand the difference between kinetic and thermal energy. Kinetic energy is the energy of a moving object. Thermal energy is a kind of kinetic energy. It's really the sum of all the kinetic energy in a group of particles. So you really can kind of technically use either term, but in order to keep things clear, it's usually better to use the term thermal energy when we're talking about the movement of particles, and kinetic energy, we're talking about the movement of the object, like a ball flying across the room. So the ball flying across the room has kinetic energy because it's moving. It has thermal energy because the particles inside that ball are also moving. They're vibrating. Now there is a catch though, and that catch is absolute zero. Absolute zero is the temperature at which all particle motion stops. It is 0 degrees Kelvin, which is about 250 degrees below zero. Sorry, 450 degrees below zero Fahrenheit. The problem, went too far again. The problem is there is no real absolute zero. It's impossible to reach it. Absolute zero is still theoretical. So there would still be some motion in something if it got right up against absolute zero. But in theory, particle motion would stop at absolute zero. It's just that it isn't real. It hasn't been achieved yet. So we're not completely sure. All right, now the most basic way that we classify matter is solid, liquid, gas, and plasma. Solid, liquid, gas, and plasma. So of all of these, the one we talk about the least is plasma, even though plasma is actually the most abundant of all of these states in the universe. 99% of all matter in the universe is plasma. Anybody know why? How could it be? Cheyenne.
The stars.
I'm sorry, say again?
The stars in the universe.
Not the size.
The stars.
Oh, I'm sorry. I thought you said size. Yes, the stars. Stars exist as plasma. Stars like our sun exist as plasma. So that's why plasma makes up 99%. But there aren't any stars on the earth, right? The closest star is our sun. So there's not a lot of plasma on the earth. So when we're talking about, for this class, for what we're going to be learning, we're talking about things that are on the earth or in the general vicinity of the earth. So we won't talk a lot about plasma, but I want to talk a little bit about it today, about what it is. Plasma is a lot like a gas, but it's actually has more energy in it. So imagine there's a gas, like the air that you're breathing, right? There's particles moving all around in the air that you're breathing. Well, in plasma, those particles have even more energy. In a gas like the air, the particles have so much energy that they're pretty spread apart from one another. The atoms and molecules are spread apart from one another. In plasma, they have so much energy, the particles themselves begin to break apart. The electrons break off of the atoms, leaving behind protons and neutrons. Now, when a gas gets really hot, like in the sun, or when there's an electric field that is run through it, the atoms inside start losing the electrons. The free electrons and the atom parts that are left over, the ions is what we call them, they create a gas that acts, a mixture. It's not a gas. It's a mixture that behaves differently than gases do. That's what we call plasma. Now, we find plasma not just in the stars. We also find it in some other pretty cool places too. You can on Earth find plasma in flames where it just gets so hot that those atoms start breaking apart. The electrons come off of the atoms. You find it in lightning. Yeah, lightning is composed of plasma. So are auroras, like the northern lights. Have any of you ever seen an aurora borealis, the northern lights? They're really beautiful. The sky actually looks like that. I've seen it a few times in my life, but not many. You have to be pretty far north in order to see them. But there's plasma in the atmosphere, and that's why we get this color. When welders put things together using a welding torch, the welding arc has plasma in it. So do neon signs and some fluorescent lights. So what happens is there's the tube in this neon light is sealed, and there's a gas inside that, and they run electricity through the gas, and that electricity excites those particles that are in the gas and causes them to break apart. So a fluorescent light, like you may have fluorescent lights in your room, you may have seen them in some stores like this. Fluorescent lights generate light because all of those particles collide with one another. The electrons are bumped up to higher energy levels and then they fall back down. I know that a lot of this doesn't mean a lot yet. We'll be learning about it. It'll mean more as we go on with the course, but just know that fluorescent lights often generate light because of plasma. And our sun, of course, is the star that is closest to us that is in the plasma state. There's also a toy that you can buy. They're not very expensive. They're fun toys. They're called plasma balls. Do any of you have one or have seen one? Sometimes science museums have big ones and you can touch them. It makes your hair stand straight up. Well, plasma balls, like these, are glass spheres that have an electrode in the middle. So I have one. I'm going to show you. This is my plasma ball. And you can see right here, it's a sphere. This is a glass sphere, and it's got this electrode. That's the stalk in the middle. And that generates energy. It puts out energy, and that energy creates plasma. It causes the electrons to break off. So I'm going to turn it on now so you can see it. There you go. I'll have to hold something behind it so you can kind of see. Can you see the movement of the plasma inside there as the electricity is running through those strands? Now, when I touch it, now what I've done when I touch this plasma ball, see the difference? I'm not touching. Now I'm touching. Not. Now I'm touching. And I can do it in a couple of different places and it'll cause it to move. Well, what happens with this, the electrons that are in there are trying to get out, and they're actually coming out through the glass. They're coming out into the air. When I touch this, it creates a path that is really easy. There's very little resistance now. So the electrons are coming into my body and they're flowing through my body and into the ground where my feet are. Now, the electrons that are inside there, remember what electrons are. They have negative charges, right? They're a negatively charged part of an atom. Those electrons, because they're negatively charged, they don't want to be near each other. They're jumping all over the place, trying to get as far away from one another as they can, because negatives repel negatives. So these electrons want to get away from each other, and they choose the path of least resistance in order to do so. That's my hand. The electrons move up and out of the ball. Yeah, Tesla actually, Wick, is the one who created the plasma ball. This was his invention. It is like a plasma coil. So there's an electric field that's being generated by that electrode in the middle, and it excites the gases and it causes it to light up like this, even though it's really not connected here, you know, to anything but me. Yeah. All right. Now take a look at the ones on the screen there. One of them's green, one of them's pink, and one of them's blue. Mine is kind of a purple color. It's kind of got a little purplishness to it, if you can see that very well. So why do you think? Why do you think they come in different colors? How come plasma balls make different colored sparks? Nyla?
Because there's different gases.
There's different gases. That's exactly right. There's different gases inside them. So these are the most common ones that would be used inside a plasma ball. There might be neon inside there. Neon will give you a reddish orange color. There might be argon, and that's going to give you a bluish violet. That's probably what's inside mine, because it's that bluish purple color. Krypton produces white. Helium produces like helium is going to give you more of a white light, but helium and xenon are usually found in those ones that are in a science center. So they'll be really big. If you ever go to a science center and you see one of these, when you touch it, you can see the hair on your arm stand up. You can, because of the electrons that are running through your body in large numbers now, the hair on your head might even stand up. And if you touch someone else while you're touching the plasma ball, you'll shock them because of the movement of electrons. So usually it's helium and xenon that are found inside those ones that are in museums and science centers and stuff. And then nitrogen is another one. So these are the colors, these are the gases that you would find inside a plasma ball, and each one of them is going to give different colors. Now take a look at these right here. The ones that are, the elements that are in this line right here, they're pretty cool. Anybody know what those are called? The ones that are in the very last column there of the periodic table. We'll learn about those in a couple of weeks. They're called noble gases. That's because they're very, very stable. They don't want to make any kind of bonds with anything else. They're happy all on their own. And they're what's used inside the plasma balls primarily. Now, we said there's solid, liquid, gas, and plasma. But did you know there's actually a couple more? There's a couple more besides those four. There are Bose-Einstein condensates. time crystals, neutroniums, and quark gluon plasma. Now, scientists have found these under very extreme conditions. So they're not an important part of the 4 states of matter. They become important if you get into an advanced physics class, maybe an advanced high school, definitely an advanced college physics class. You would run into those. But what is dark matter? Dark matter is a little, I'm not sure how to, let me see if I can get a good explanation of dark matter. This is where, yeah, AI comes in really nice and handy. So dark matter is entirely invisible, emitting no light or energy, making it undetectable. It's mysterious substance. Yeah, that's why it's hard to define. It's a mysterious substance. It affects the universe, but we're still trying to figure it out. So yeah, it's not a particle. It is not a state of matter like that. So again, we do have these states of matter that can be generated under extreme conditions, but we live on Earth here. So we try to study the matter that's on Earth. And since plasma is pretty rare on Earth, we're not going to spend a lot of time talking about plasma. We will focus on, so we'll get to that, Wick. We're going to talk about that in a minute. That's what the oobleck is a kind of a semi-solid. All right, so we have these 3 states here on Earth. We have the 3 states of matter, solid, liquid, and gas. And those are categorized by how the particles are arranged. Look at the difference between the arrangement in the solid, how they're nice lines and rows and columns, and they're all kind of in a row. And then liquids are changing places with one another. Those particles, atoms or molecules, are swirling around and changing places with one another. That's why water inside a glass sloshes around, because the particles are moving over each other. And then in a gas, they have so much energy, they just are bursting away from one another. They go out into whatever it is that's holding them. So the state of matter depends on the arrangement of particles and the energy of the particles and the distance between the particles. So solids are going to have a very fixed shape. They're not going to change their shape. My mouse is not going to change shape unless I put so much energy into it that it melts. Then it will. But as long as it doesn't hit that point, it's going to stay solid. It'll have this fixed shape and fixed volume. The particles in this solid are going to vibrate, but they don't move out of position. It doesn't change shape at all. Liquids, on the other hand, their shape changes as you put them into a different container. I've got this little cup of water right here. If I were to pour this into a big wide container, it would take the shape of that container. If I poured it into a round bowl, it would take the shape of the round container. So those particles can move around. They do have a fixed volume because we can't change the amount of water. We can't compress them and make their volume less, but the shape does change. Gases do whatever they want. Gases have so much energy that the particles vibrate and they break away from one another. They don't have a fixed volume. They don't have a fixed shape. They just simply expand to fill up their container. So this is kind of what the solids look like. The particles are going to be real tightly packed together. They're going to vibrate, but they're not going to move out of position. They have a fixed shape and a fixed volume, and they don't have much kinetic energy at all. On the other hand, liquids can flow. Liquids do have a fixed volume, but they do not have a fixed shape. They change shape with whatever the container that they're in is. Now, they are tight to one another, but they're far enough apart that they can move over each other. They can trade places, just like you see in the picture. They take the shape of their container and they're attracted to each other. So see how these come back together? They're attracted to one another. So they come back together after they've come apart like that. Here's a real cute little joke. Have you guys, read out here that liquids take the shape of whatever container they are in, but they maintain a constant volume? So we know cats are liquid. They take the shape of their container. Isn't that cute? All right, and here's a phase change joke for you. Well, that was it. We'll get to a different one in a minute. So the more pressure we put on a gas, Gases are next. Let me put all these on quickly. Gases don't have a fixed shape. They don't have a fixed volume. They're very far apart. The room you're in is filled with gas. There's lots of different particles of gases that are in the room that you're in. They're far apart. They're moving freely. They're not bonded to other particles, and they can be compressed. We can put pressure on a gas to make its volume smaller. The less pressure we put on it, the greater its volume is going to be. The more pressure we put on it, the less its volume is going to be, because particles of the gas move all the way around evenly. So gases have more kinetic energy than the other two. Gases have more kinetic energy than liquids, and definitely more kinetic energy than solids do. So remember what thermal energy is. It is the kinetic energy of the particles. Even if an object isn't moving, the particles are. The particles in a solid vibrate a little bit. The particles in a liquid vibrate a little bit more. The particles in a gas vibrate a lot. We're going to use that term thermal energy in order to describe the kinetic energy of the particles. All right. Now, here's a little riddle for you. Before I'm born, I am liquid. When I am alive, I look like a solid. When I die, I am a gas. What am I? Not water. That's a good guess, though. And you're kind of on the right track. Kind of on the right track. Correct answer is a bubble. A bubble. So a bubble is a round particle of one substance trapped inside another. So when it's born, it's liquid, or before I'm born, I'm liquid when it's in the bottle, before it becomes a bubble. When it's alive, when it is a bubble, it looks like a solid. That looks like something solid, right? And we've definitely got some solid nature to it. But then when it dies, when it bursts, it becomes a gas. So do you guys know why bubbles pop? They pop because what a bubble is it's a pocket of gas surrounded by two layers of liquid soap with water in between the layers. So think about that. That bubble has two layers of soap and there's water in between the two layers. If either the inside layer or the outside layer pops, the whole bubble pops because the gas then goes out into the air. So bubbles will pop when they come into contact with something solid. They can also pop without ever touching anything. So think about that. How can they pop without ever touching it? Think about what they are. Two layers of soap with water in between. What happens when that water changes? The water evaporates. That water in them is going to evaporate away. And that makes the film layer, heat. Yeah, the heat is what's going to cause that water to evaporate, whatever the temperature of the air is. So the film is going to get weaker and eventually it will pop and those gases will escape back into the atmosphere. All right. So one thing to keep in mind is that what we mean when we say heat is the transfer of thermal energy, moving from one object to another. So that movement of the thermal energy, the movement of those particles, can be moved to a different object. That's called heat. Heat is the transfer of that energy. And thermal energy is always going to move from something warmer to something cooler. The hot thing is going to become cooler. It's going to move from the hot thing to the cooler thing. Now, when thermal energy goes up, the water can change phase. It can go from solid to liquid or liquid to gas. We have phase changes due to increasing thermal energy, and we have phase changes due to decreasing thermal energy. So this page right here shows you the increasing thermal energy. So let's start with a solid. As we increase thermal energy, it goes to a liquid. It melts. We call this process melting. Think of ice. Whenever you're thinking of states of matter, I find it useful to think of the states of water. So we have ice, liquid water, and then water vapor. So when we go from solid, like ice, to liquid water, that's melting. The ice cube melts. Now, when liquid goes to the vapor state, we call that vaporization. It gains thermal energy, so it goes from the liquid state to the gas state, vaporization. There is a process, though, where something can go from being a solid directly to becoming a gas without ever becoming a liquid at all. That process is called sublimation. So have you ever opened your freezer and your ice cubes are really small? Like you wonder, how did these ice cubes get to be really little? They're not as big as they should be. That's because they went directly from being solid to being gas. Part of them did. So they have sublimated and now they're smaller. The water molecules went out into the air inside your freezer. Those are due to increasing thermal energy. Can go the other way too, though. Decreasing thermal energy. We have phase changes from gas to liquid to solid, or directly from a gas to a solid. So again, think about water when we're talking about this. Think about when we go from gas in the air, water vapor in the air, to where it condenses onto the leaves or on maybe onto the side of a glass. We would call that condensation when it becomes liquid water. Then when the liquid water gets colder, it loses more of that thermal energy. It's going to become a solid like ice cube in the process of freezing. But it can also go directly from gas to solid in the process called deposition. Deposition. So those are the phase changes, the primary phase changes due to decreasing thermal energy and increasing thermal energy. All right, I want to take a break. We might come back to this, but I want to make sure we have time to do the oobleck. If you didn't bring the materials for the oobleck, that's fine. You don't have to do them. I will always let you know if something is required to do here, and I'll give you plenty of heads up before that it is a required activity. So you can just observe. I'm going to tip down my computer, my camera, so that you guys can see what I'm doing here. So here is my bowl. Here is my cornstarch. I'm going to pour the cornstarch into the bowl. So you guys can go ahead and do the same thing. If you have yours, pour the cornstarch into the bowl. Kind of sticking. All right, there's my cornstarch. If you don't have the full amount of the you know what, I'm going to turn this off so that you can see. Let me stop the share so that you can see the whole thing. So if you don't have the full amount of the 1.5 cups of cornstarch and a cup of water, you can use less. You can use just a little bit of cornstarch and a little bit of water. So you also then need to have the bowl to mix it in, the spoon, and it's kind of messy. So I always recommend bringing some kind of rag, paper towels, or a washcloth to clean up. All right, if you wanted to, you could bring food coloring to make it colored, but I didn't here. So what I'm going to do is I'm going to pour about half of my water in. I don't want to pour all of it in because I don't want to use too much. So I'll pour about half of it in, and then I'll stir it around. And you'll begin to notice right away that as you stir it, it gets hard to stir. It like doesn't want to stir. It resists the attempts to stir it with the spoon. Now this phenomenon, this sticking like it's doing, this is called shear thickening. It's when it stiffens or gets stiff in response to stress. In this case, the stress is my stirring it. So take a look at how hard this is. As I bring it up, it becomes liquid and it pours right back out again. When it's not under any kind of stress, it becomes liquid. So I'm going to try and stir most of this in and try to make and you can just see how it looks like it's solid, but then as soon as I let go, it pours right off the spoon and becomes liquid. All right, if you're not able to do this today, you can do it at any point at home that you have some cornstarch. That's really all you need is cornstarch and water. I'm going to put just a little bit more water in now. I don't want to add it all because if I make it too thick, then it won't work. It won't do what it's supposed to do. All right, now, in order to be able to pick this up, I kind of have to go at it kind of slowly to be able to move it. And then I can pour it onto my hand. And as I move this around, you can see I can actually make a ball with it. but I have to keep applying pressure. The very second that I take the pressure off of this ball that I'm rolling, watch what happens. It becomes liquid and it pours right out through my fingers. I can do it again. I'll pick up a larger chunk and see if we can get a bigger amount. See what I mean with it being kind of messy? And the minute I stop putting pressure on it, it pours back into the bowl. All right, so let's make this a nice bigger ball here. As I roll it, so go ahead and try and roll it if you can, like that. So this is not really solid. I'm not making a solid and then turning it into a liquid. This is one of those kind of like Wick was talking about, the semi-solids. So watch again, I'm going to let go of it and you can see that it turns into a liquid, pours right back out of my hands. It's really pretty cool to do. All right. So like I said, it's not really a solid, but it does take on some of the properties of a solid. So at the places where we apply force, like when I'm using the spoon and I'm trying to stir it, I'm applying force to that. What happens is these cornstarch molecules get smashed together and they trap water molecules in between them. So temporarily, this becomes a semi-solid. Now, there's a lot of mysteries with this oobleck. We call it a non-Newtonian fluid because it doesn't really follow the laws of physics. It kind of trades back and forth. And researchers still really don't understand all the mysteries behind oobleck. They don't know whether those cornstarch particles actually touch each other or not. They don't know what causes them to separate when the pressure's taken off of them. We don't know whether or not if we have larger grains of cornstarch, that would affect the way that it behaved or not. We just know that it's fun to play with. It's pretty cool. And it gets its name from a Dr. Seuss book. The name of the book is Bartholomew and the Oobleck. So in that book, there was a gooey green substance that fell from the sky and caused a lot of trouble in the kingdom. Now you can see this is losing water. So it's doesn't take quite as much, because the water's evaporating off of it. It doesn't take quite as much pressure to keep it in the solid state. But again, as soon as I let go, it becomes a liquid and it pours right out of my hands. All right, so now hold on a second. I'm gonna wipe my hands off and then tip my camera back up. I don't want to touch the camera with hands full of cornstarch. This is pretty easy to clean up. All you have to do is get it wet, run your hands in the sink. This can go right down the sink. It's not going to cause any trouble. As long as you flush it with plenty of water, it's not going to cause trouble in your sink. All right, so there we go. All right, so can you guys think of any uses for something like this? What use might there be in the world for an object that would stiffen when pressure was applied to it? Any thoughts? What about a bicycle helmet? Imagine if you could have a bicycle helmet that had that became stiffer when you hit the pavement and it provided some shock protection for your brain, or crash protection in cars. What about bulletproof vests? Imagine a vest that, there we go. Imagine a vest that when the bullet hit it, it became solid and it stopped that bullet completely. Mohammed.
I have a question and I have an answer. I think they should also be making like walls, because like if someone tries to like hit it with something, it could like become a solid. But my question is it okay that you can repeat the instructions to make oobleck?
Yes, I will. So
Thank you.
really all you're going to do, you're going to take 1.5 cups of cornstarch and 1 cup of water and mix them together. That's really all there is. I'll type it into the chat box here. Hold on 1 second. Let me see. I think this will work. Nope. Nope, that did not work. All right, I'm going to type it in. So you just, the secret is don't add all your all your water at once. See, I had a cup of water, but I only really used 3/4 of a cup. I have that much left in order to make it because it's gonna, depending on your cornstarch, it might not take as much or it might take more. Okay, so 1 cup cornstarch. Oh no, sorry, 1 1/2 cups cornstarch. 1 cup water. Stir until mixed. Yeah, and then you just play with it. You keep on playing with it until it is done. So there you are, 1 1/2 cups cornstarch, 1 cup water. If you want to add color, you can put some food coloring in it. Yeah, great. Wick. Yeah, I'm not hearing you. Was anybody hearing Wick when he was talking? Is it? No. And I think maybe your microphone is turned off or muted. It's not muted in Canva or in Zoom. That's working fine. But yeah, you can do this. This is fun. So sometimes you can just take like a tablespoon, take a tablespoon of cornstarch and a 1/2 tablespoon of water and mix them together. You don't have to use this large amount like this. It's just more fun to play with when there's a large amount. And if you can put it in a tray, I'm gonna tip this down again and show you guys something. Yeah, pretty cool looking now. Okay, so there we go. So you can see here how it's really looking like it's got solid to it, but then it goes right back to liquid. So one thing that you can do when you're playing with this is after you've stirred it pretty well, you can actually hit it with your hands and it'll stop it. But if you take your fingers and go real slowly, they'll go all the way down to the bottom of the bowl. And as I pull, I have to pull slowly up. So if I push them all the way down to the bottom of the bowl slowly, but then I lift up quickly, I pick part of it up with it. But if I lift up real slowly, it pours right off of my hands again. It's just fun to play with. I think oobleck is fun. It's something that you know, especially if you got a little sibling, that they might enjoy playing with a little oobleck right before bath time. Right? All right, Wick, did you get it working? Do you still have a question?
Can you hear me?
Yes, now we hear you.
Yeah, so I was thinking if we made a helmet out of oobleck, since we're not applying pressure when we're wearing the helmet, won't the helmet just drip down?
You'd have to have it sealed inside there. And it could be a challenge because it would kind of slosh, right?
Yeah.
So there would have to be some pretty good engineering behind that. One of the students in the first section yesterday or Monday, yesterday, was telling me that he read that they were starting to use this on roads, a similar, not cornstarch, but a similar kind of a process on roads for speed bumps. That if a person drove over it slowly, the bump wouldn't stop them. It wouldn't slow them down. But if they hit it too fast, it actually slowed their car down. It became more of a solid. So this is called a non-Newtonian fluid, and this is not the only one. There are other non-Newtonian fluids. This is just one that we all have in our house. There's also a non-Newtonian fluid that you guys probably use every single day. Hopefully you use it every single day. Anybody have any guesses what non-Newtonian fluid you might use every day? Soap is a good guess. It is not soap. Soap's a little bit different. Soap doesn't change state. When soap isn't like think of it as being more semi-solid. Soap is not really a semi-solid. Toothpaste. Toothpaste is a non-Newtonian fluid. It is solid enough because of the particles that are in it to give it a little bit of that solidity. It doesn't ooze down, but it also is liquid enough to squeeze out of a tube. So it is considered a non-Newtonian fluid. Yeah, excellent. All right, everybody, we're done for the day. It was great. Anybody have any questions? Keep playing with your oobleck if you made it. If you didn't, try it before next time. It's just kind of fun to turn the science into reality. All right, if you have any questions, you know where to find me. Have a great week, everyone.
Thank you. Goodbye.
Thanks for coming. Bye.